Our planet. For more than 4 billion years, it has provided all life forms with the water they need. But the recent explosion in human population is now straining this natural resource to the limit. Night and day, we're making use of the gift of nature that we need most to survive. But night and day, we're also polluting it. When bad things happen to our fresh water, it is easy to overlook. Out of sight is out of mind. At least for most of us. When bad things happen to our fresh water, who really knows what it looks like? Who really knows what it smells like when you get close to it? Who really knows that wastewater has to be taken care of as soon as it enters the labyrinth of waterways and reservoirs underground? But also, who really knows that wastewater still holds resources that can help us find solutions for some of the world's most pressing problems? When fresh water enters urban areas, it not only serves as a source of drinking water, it also becomes a vehicle to transport the waste that is produced in these areas. The waste comes from many different sources, from industry or from businesses. Waste that comes from municipal hospitals or from local restaurants and pubs. And of course, it is waste that comes from private homes. Municipal wastewater transports a wide variety of organic and inorganic pollutants into the dark and complex world of canals and pipes underneath our cities. Oils and solvents, detergents and personal care products, medication residue and pathogens, and, of course, human waste. Just imagine the complexity of this cocktail of solid and liquid waste as it is flushed towards the wastewater treatment plant nearby. Just imagine the job that will have to be done there to make sure that all that waste that is gathering underneath our cities is not released back into our environment. Every single drop of wastewater that enters the treatment plant goes through a complex purification process. In the fully computerized control room, the plant operators are busy 24 hours a day to make sure that all operations at the plant are running smoothly and, of course, to supervise the immense intake of wastewater.
We have to imagine the inflow into the wastewater treatment plant as a big stream, bringing in at least 3,000 litres per second when there is normal weather like today. So it's certainly not a little stream by any means. When it starts to rain, though, the stream swells and turns into a big torrent. Then the whole wastewater treatment plant has to deal with 10,000 litres per second.
Wastewater treatment starts at the rake. Here, unwanted waste that would otherwise clog pumps or damage moving equipment is being fished out of the water. Nearly 15 tons of coarse dirt is collected daily to be disposed of at a landfill outside the treatment plant. Inside the grit collector, not only sand, gravel and rocks are gathered, but also greases and oil. Now the impurities inside the water take the form of sludge. The so-called primary sludge sinks to the bottom of the primary clarifier, while the water is forwarded into the activated sludge tank. Here, billions of microorganisms are busy feeding on the organic matter carried in the water to clean it up the natural way, but not without a little help from extra oxygen that is blown into the tank.
Two important steps in the wastewater treatment process are mechanical purification and biological purification. The mechanical purification process produces sludge in the primary clarifier, and in the biological purification process there is this bacteria sludge. Both sorts are then further treated here on the plant. They're thickened first and then decomposed in the digesters.
The digester towers of a wastewater treatment plant play an important role when it comes to further processing the sewage sludge. Inside these airtight constructions, The sludge that has been derived from mechanical and biological sewage treatment will be converted into gases and residual biomass. While the concentrated substance of solids and organic matter is constantly mixed, it is decomposed by anaerobic bacteria. Bacteria that only grow in places where there is no oxygen. There are billions of bacteria inside the sludge. There may be more than 300 different species. Some of these bacteria decompose fats, cellulose and proteins into soluble compounds. Others transform these compounds into organic acids. A third set of bacteria completes the decomposition process. These so-called methanogenic bacteria take the organic acids and convert them into gas, more precisely, into biogas. Biogas consists mainly of methane, but it also contains carbon dioxide and small amounts of other gases such as hydrogen sulfide. Once the gas has risen to the top of the digester tower, it is directed into a gasometer, where it is stored for further use.
This methane gas is then purified, stored temporarily, and then used to generate power and heat, which we can reuse entirely here on the wastewater treatment plant.
So, the sludge that is fermented in the digestion towers is not only waste, it can also be used as a source to generate renewable energy. With oil and gas being limited sources of energy, and more greenhouse gases being emitted into the environment, alternatives to fossil fuel sources are becoming indispensable. Alternatives that are CO2 neutral and climate friendly. Alternatives that lower the ecological and economic risks our society is exposed to in Europe and worldwide. Wastewater treatment plants can lower their energy uptake from the public power net considerably if they are equipped with the technology and the facilities to generate biogas from sewage sludge. This wastewater treatment plant is almost self-sufficient in energy terms, but also the construction of an innovative facility on the site designed to upgrade the valuable waste gas has proven to be worthwhile in several respects.
That waste is not waste, that waste can be utilized as a source, has a sustainable aspect. It has a financial aspect, which is important, but it has an ecological and economical aspect as well.
But to install and operate facilities that can enhance a sustainable wastewater management is quite an investment. Digesters, where biogas is produced, and gasometers, where biogas is stored, are not found in every wastewater treatment plant. Neither are biogas upgrading facilities. But upgrading biogas is crucial. For example, when the aim is to generate an alternative to fossil fuel combustion. Biogas can only serve as an alternative to petrol or diesel after it has been cleaned and purified in an upgrading facility. Inside this labyrinth of pipes, pumps, compressors, collecting vessels and storage tanks, the quality of the raw biogas is enhanced until it is of the same quality as natural gas. When the biogas flows into the upgrading facility, it contains approximately 60 to 70% of methane. But it also contains impurities that need to be removed. In the first stage of the upgrading process, the biogas is treated in such a way that all its components are evenly distributed. This is because, in a balanced mixture of gases, the individual components can be separated from each other far more easily. Once the gas mixture has been compressed, the actual biogas treatment process, the elimination of the impurities, can begin. As the first step, water is removed from the gas mixture. Secondly, hydrogen sulfide is taken out. And finally, carbon dioxide is eliminated from the gas mixture and returned to the environment. Now the biogas has a methane content of at least 97%. The upgraded biogas, also called biomethane, is placed in intermediate storage and can be fed when needed into the public natural gas grid. From the producer straight to the user, to set a whole fleet of city buses in motion, as here in Bern, Switzerland. Every day, each of the nearly 100 buses of this public transport company has to be filled with biomethane. Every day, this fleet of city buses is running on a fuel that does not add any additional CO2 to the environment. A sustainable biofuel, which was not produced from natural resources such as plants and crops, but from wastewater sludge instead. Waste that would otherwise have been burned and disposed of in the environment. Wastewater does not only play an important role when it comes to generating renewable energy such as biogas, it is also gaining increased attention when it comes to the recycling of nutrients. Nutrients for plants, for instance. While the sludge that is pumped into the digester towers can be used as a source of biofuel for vehicles, the residual sludge that is pumped out of the digester tower counts as an important resource when it comes to sustainable agriculture. But residual sludge is not allowed to be used as a fertilizer in most of Europe anymore, as it once was in the past. Why? Because residual sludge not only contains valuable nutrients for plant growth, such as phosphorus, it contains toxic pollutants as well. So what can be done with the sludge generated from wastewater? How can the phosphorus be preserved while the organic and inorganic pollutants inside the sludge are eliminated? Removing the water from the sludge is the first step. But even centrifuged and dried sludge still contains toxic contaminants, such as antibiotics, endocrine disruptors, or heavy metals, apart from the valuable plant nutrient phosphorus. At temperatures of 850 degrees, the organic and most of the inorganic pollutants are destroyed. The bad news, except for heavy metals. The good news, the phosphorus is still there. So, sewage sludge ash still contains the treasure that could be utilized for sustainable agriculture. Scientists are looking for ways to recover this treasure. After all, the world's supply of raw phosphorus is diminishing, and new possibilities have to be opened up to recover phosphorus from sewage sludge ash and to produce recycled phosphorus fertilizer.
These procedures aimed at recycling phosphorus from sewage sludge have to try, of course, to disrupt the structure of those phosphorus compounds, creating new compounds from them that are biologically available. They also have to be able to remove any residual heavy metals from sewage sludge ash.
Therefore, not only are heavy metals still polluting the sewage sludge ash, but the valuable phosphorus compounds inside this precious powder are still not in the chemical form that would enable them to be easily taken up by plants as a nutrient. Thermochemical treatment helps scientists to deal with these challenges. First, magnesium chloride is added to the ash. The magnesium inside this powder will react with the phosphates inside the ash. The chlorides will react with the heavy metals. For these reactions to take place, the mixture has to be exposed to heat. So, a small-scale rotary furnace comes into play, which will bring the scientists a considerable step forward in their investigation. Inside this furnace, at a temperature of 900 degrees, heavy metal chlorides are formed. Due to high vapor pressure, these chlorides evaporate and transform into the gas phase. This is how they separate from the ashes and eventually can be removed. At the same time, new mineral phosphate phases are created, with a higher bioavailability than the phosphorus inside the sewage sludge ash collected from the treatment plant.
We have been examining this thermochemical process for many years now and have achieved quite a lot with our research. The depletion of heavy metals works very well. We managed to remove ecotoxicologically relevant heavy metals such as lead and cadmium very effectively.
Of course, the ultimate aim of the scientists is to develop a methodology of how to produce a fertilizer with recycled phosphorus as its main ingredient. Does such a fertilizer have the same bioavailability as a fertilizer made from natural phosphorus resources? And if so, does a fertilizer containing recycled phosphorus from sewage sludge represent a truly viable alternative to conventional fertilizers made from phosphate rock? Producing recycled phosphorus fertilizers in the laboratory and comparing them to conventional fertilizers is at the core of European research programs, for important reasons.
The European Union has no relevant phosphorus resources, which means that the EU is completely dependent on the phosphorus world market. And phosphates are distributed very unequally across the world. They are mined in only very few countries. 70% of rock phosphorus reserves, for instance, are located in Morocco and the Western Sahara. This means that in future, the European Union is going to have to give a lot of thought to how phosphorus can be cheaply obtained. An effective system for recycling phosphorus would be ideal here, of course. And our vision is to take the method we are currently developing, have it compared and evaluated, and then have it implemented on a large technical scale, with the result that Europe can, as it were, build its own phosphorus mine by using this recycling method.
While some scientists conduct laboratory research to investigate methods for the recovery of phosphorus from sewage sludge ash and the production of recycled phosphorus fertilizer, other scientists conduct field experiments. Their aim is to compare the performance of different samples of fertilizers produced in the lab with each other and, of course, with the performance of conventional fertilizers.
In this experiment, we're testing various phosphorus fertilizers, which differ in the origin of their phosphorus as well as in their composition. Here we have phosphorus fertilizers, typically originating from a North African mine, and we have a recycled phosphorus fertilizer, and also different contents of nitrogen in these phosphorus fertilizers. And the experiment is aimed at showing the differences between these phosphorus fertilizers. This strip of land has not been fertilized with phosphorus, so this enables us to make comparisons. Here you can see a substantial difference in growth compared to the strips of land with phosphorus fertilizer. They are also slightly higher, stronger too, dark green in color. And they also have more cobs and also bigger cobs. In the strips of land with phosphorus fertilizer, we cannot see a difference between the recycled phosphorus fertilizer and the conventional phosphorus fertilizer mined in northern Africa. They all look the same.
Wastewater. It contains more than pollutants. And wastewater treatment plants. They have the potential to do more than just remove waste.
When there are more wastewater treatment plants installed worldwide, there is a huge amount of biogas which could be utilized, and of course also nutrients like nitrogen and phosphorus could be recovered as natural resources.
Finding and producing alternatives to natural resources is a challenge that will not go away, and it is scientists and engineers that are at the forefront to find solutions.
Some of the processes for phosphorus recycling from wastewater, sludge or sewage sludge ash are on the brink of large-scale industrial implementation as part of an EU project that is currently being launched. We'll be in charge of running these pilot facilities, we'll be taking samples and analyzing them. We'll also be measuring the power requirement and finally be able to establish which methods are most promising for the future.
Water has always been the source of life. No matter in what condition, it may even help us now to find solutions for some of our most urgent problems worldwide.